Welcome back to the series where I tried to code an RTS without using a pre-built game engine. In the last episode, I got a basic engine working where a player can select units, move them around, and attack enemy units. For this episode, I'm programming some terrain and giving units pathfinding instructions. And like the last episode, I'll end with a battle. So if you get bored while watching, maybe skip to the end to see the action before you go. Before developing terrain, I continued making some other changes that I think are useful to have in an RTS, but wouldn't make for much interesting content to do the process. Here's what I changed. 1. Holding shift will prevent units being deselected, allowing the player to add new units to their selection. 2. Selected units show where they're going. 3. The player can zoom their camera. I even made it where the camera's zoom is anchored to where the mouse is pointing to. That last change was a lot harder than you might expect. I think I tried for an hour to get it fixed, but then I realized, you see these two lines of code telling the program to adjust the camera scale and location? Turns out the order matters, and I specified them in a way that was contrary to how I was thinking of the camera in my head. So I decided to swap these two lines and bite the bullet. I struggled to rewrite the zoom code, and then I pulled out a sheet of paper to work it out visually and sort through the algebra. It took me like 15 minutes then. Maybe I should have done that sooner, but at least the zoom function is working as intended and it feels nice. I might make it smoother later, but that's not what this episode's focus is. Okay, terrain. I want the terrain to be more than just a flat plane. I established a byte variable to represent different types of terrain and then give each of these terrain types a color. At the start, the tiles are all random. How about making the terrain more interesting? Some time ago, I made a program that generates more realistic terrain. The terrain is randomly generated, but clearly the randomness is not purely chaotic. There are concentrated masses of the same tile type. How did I do this? Basically, the program draws some big circles at random locations and then draws more layers of progressively smaller circles. The circles on the next layer are smaller, less intense, but also more plentiful than the circles of the previous layer. After some copy, paste, and adjustment, the code works for my new project. For this image, I decided to render the circles so you can see them. You can see two circles clearly influencing the terrain. The map is not as detailed, and that's because I'm using the old circle count on a program that has a bigger arena size. I changed the variables, and cool. The terrain isn't very smooth. There's a lot of lone ponds and small islands. That's because I didn't copy over the smoothing code. That allows the tiles to reference neighboring tiles to make themselves even more smoother. But for now, I'm omitting that part of the code. Maybe it'll make for better testing of unit navigation. But I'm not doing the unit navigation AI yet, because right now the units don't have collision rules for the terrain. To do that, I first made a new class called Obstacle. You might be wondering why I don't just use the tile class as my obstacle. It's because tiles aren't the only barriers. Later, when I add buildings, I can give those their own obstacles and then handle both terrain and building obstacles with the same code. You can now see red boxes overlapping the water and the dark brown. These represent where the obstacles are. Now that the obstacles exist, I can head back to the class that handles unit collision and program a collision check for units versus tiles. The code I came up with handles the units as if their collision area was a square instead of a circle, simply because it was easier to program it that way. I might change this later. If a unit is colliding, I basically divide the obstacle into 4 areas, and depending on the one that the unit is in, I send the unit to a different edge of the obstacle. It looks like it's pushing too far, and I troubleshoot. This iteration seems disastrous, but notice how only the units trapped in an obstacle area are getting the weirdness. For the other units, they move fine and properly collide without a hiccup. If I don't create units in obstacle areas, I should be fine. I changed the way that units come into the program. Now I can manually add units at specific spots. This is useful for setting up specific scenarios and writing useful messages. Now that I have obstacle collision working, it's important to give the units better navigation instructions. But first, I admired the beauty of the program so far. It was satisfying to see the units crawl across the landscape. Okay, that's enough. Time for unit navigation. First, I want some way to just have the unit remember multiple lines as the path that it takes. To do this, I make different commands to be their own classes. This might seem strange, but my idea is to have the unit break down the general move command into smaller move commands. Now that a command is its own object, I can make an array list inside the unit class to remember a list of commands. It took some code rework, but I got it working. I also added a theta value to units. So I have a way to store a bunch of move segments. How do I tell the program to arrange these in a way that makes an efficient path to the target destination? Over a year ago, I was wondering how pathfinding worked. What I found was something called Dijkstra's algorithm. What happens is that there are points to travel to called nodes. There are also lines connecting the nodes. Each node has a value called v, which is the distance of the shortest found route. At the start of the algorithm, the starting node has a v value of 0 and all other nodes start their v at infinity. Starting at the, starting node, the algorithm checks each neighboring node, adding the current node's v value to the length of the segment, coming up with a new proposed v. If this proposed value is less than the pre-existing v of the neighbor node, the neighbor's v gets the proposed value. After all neighboring nodes have been evaluated, the current node becomes checked. Then, the next current node is the unchecked node with the smallest v value. And then, this next part I explain, I originally got this wrong. What I had thought about how the program ends is if the current node finds the destination node as a neighboring node, the algorithm ends. It turns out I had a flawed understanding of how the algorithm ends, but I'll get to that later in the video. For now, here's a question. How does the program know what locations to use as nodes? Technically, any point the unit can reach can be a node, even between pixels. That could mean millions of nodes with even more segments connecting them together. The solution I found was in a previous project that I briefly showed on my channel. When I click the Find Path button, the program starts by making nodes at every corner of every obstacle. If a node is inside an obstacle, it gets deleted. Then a segment gets drawn between every combination of node, and then each segment that intersects an obstacle gets deleted. This allows the program to focus on critical areas instead of every open pixel in the entire arena. Then the program performs Dijkstra's algorithm to determine the distance of the shortest path. But here's a flaw in my code that I didn't show in the video, and here's what I was talking about a moment ago. So what happened? I think what is going on is that the program checks the starting node, then the next node with the shortest v is near the left of the arena, so it checks that node next. Then, since the destination node is detected, the program decides that is the route to use. But we humans see that obviously it'd be more efficient to use this route here. I found a solution later, but I got the script in chronological order, so I'm explaining the solution later. For now, here's another potential problem. The bigger my RTS arena becomes, the more obstacles there are to handle, potentially slowing computer performance. But before I even learned what Dijkstra's algorithm was, I realized this. Since the shortest path between 2 points is a straight line, if that straight line doesn't collide with an obstacle, I could just use that line. What I eventually thought of was if there is an obstacle in the way, I could just draw the nodes relevant to that obstacle rather than the corner nodes of every obstacle. Then draw more lines and see if there's a problem then. I started to copy and paste some files from that pathfinding program into my RTS game, and I was getting intimidated. So before I even start work on the new pathfinding fixes I was just talking about, I wanted to get what I already had working in one program working in this new one. It was at this point that I remembered again that it makes sense that RTS games are less common, at least with less experienced programmers. There is so much technical coding that goes on with making this type of game. Eventually, when I tested the program with the units having a path brain, my bigger size arena had so many obstacles that the game froze when calculating. So for now, I made the arena smaller. I got the pathfinding working, but the unit doesn't do anything with the path yet. I managed to transfer the discovered path into a series of move commands. Later, I tested a theory I had for a more efficient approach to setting up nodes and segments, but after hours of trying, I wasn't succeeding. So I reversed my changes and tried other ideas I had for pathfinding. Remember that I said I had a misunderstanding of Dijkstra's algorithm? I now think the algorithm is supposed to end when the destination node becomes the current node, not when the destination node is first detected as a neighboring node. That was a quick fix, and after my use of the pathfinding in the following weeks, I'd say that problem is fixed. But something else I'm interested in fixing is eliminating useless nodes. Some of the nodes aren't of use because they're collinear between two other nodes. I changed the program so that if either of a tile corner adjacent tiles are blocked, the node for that corner doesn't get drawn. When I got this change in, I felt comfortable increasing the arena size again. It still took a moment for the program to crunch, but I got to see a visual result that looked like what I expected. Then I ran the program again, and when I gave the move order, a solar eclipse happened. Oh, I forgot to add a break line for the test segments loop. That fixed the problem, but computation is still slow. I decided to add the smoothing method to my terrain generation. That's a simple change, and I figure smoother terrain might mean less nodes to calculate. I tested it out, and it seems the performance has improved. Another idea. Right now, each segment checks every obstacle, even when said obstacle is far away. What I could do is limit the segment's collision check to a localized rectangle and check the segment to only the tiles in that box. Amazing. This specification has greatly reduced the lag that comes with giving a unit a new command. Unrelated to pathfinding, you might be wondering why some units show a triangle and others show a square. Basically, the squares fight at a close range. I'll have to figure out how to instruct melee units to pursue nearby enemy units that are still not next to it, but that's for later. I shifted gears back to the idea I was trying earlier. I changed the program so that it would organize groups of obstacles into clumps. What am I going to do with the clumps? My general idea is this. Step 1. Organize obstacles into clumps. Step 2. Draw a segment between the start node and destination node and perform Dijkstra's algorithm. If there is no obstacle interference, that's the path to take. Otherwise, do the loop described in Step 3. Step 3. Get every clump of obstacles that collides with the Dijkstra path. Make new nodes and segments with consideration to the newly found obstacles. Perform Dijkstra's algorithm again as if only the discovered clumps exist. Take the new Dijkstra path and see if it collides with other clumps. If not, that's the path to take. To try the theory, I decided to make a copy of my code and test the theory in the copy. It was difficult work. One problem I found was with some of the data used in Dijkstra's algorithm not resetting with multiple Dijkstra tests for the same command. Eventually, I got a result to what I had in mind. You can see that if there are no obstacles between the starting spot and destination, the algorithm is straightforward, while the spatial path is literally straightforward. Even when there's a clump in the way, there's a lot less nodes and segments generated. I hope by now you see the challenge to this pathfinding is not just about making something that works, but also making it efficient. It makes me wonder how many indie RTS games have poor pathfinding. Well, back to my own attempt. I compared the new method of finding nodes with the old method. And I think the new method is a lot faster for straight line paths, and even a little faster for paths with more turns. Even when a new method only gives minor performance improvement, I appreciate the progress. Remember, when an algorithm runs hundreds of times in a single game, even small optimizations add up. This might also be a nice time to explain a speculation of mine. I think in programming, simplicity does not mean efficiency. It's easy to set up a program to do a check loop, and after that, a loop doesn't get more complex whether it runs 5 times or 1,000. But if you program a more complex method that runs the loop half as much for the same result, that's a win. Computers do not fear complex instructions. It's task volume that slows them down. Another problem I have is with units sometimes catching on corners. In rare cases, the unit never escapes with its current instructions. This is because the segments do not consider the radius of the unit. I have an idea. Make the obstacle have a second box that has the dimensions of its border plus the radius of the unit. The segments will do collision checks with the secondary box instead. You can see here that the program seeks another path. The cyan line doesn't collide with the obstacle, but is still near enough. Time to address an understandable crash problem. If I order a unit to move somewhere it can't reach, the program freezes. To solve this, I thought about making more clumps but of a different type. These new clumps will be for traversable land instead of obstacle tiles. Then when I give an order to a unit, it first checks the target destination's tile to see if that tile is part of the same land clump. If it is, the unit should be able to reach the target. But there was a problem with this method, and I didn't even code the idea before I realized the problem. I plan to add buildings later, which will interfere with pathfinding. This means that a united landmass at the start of a game might become disunited when a building gets placed at a choke point. I have another idea, and this might be simpler. Building off Dijkstra's algorithm, I think that if a node's v value equals infinity, it means the algorithm hasn't found a path to it yet. And if there's no unchecked node with a v value less than infinity, that means the algorithm has run out of options and should therefore terminate. That was a satisfyingly simple fix. I also fixed a problem where obstacles from undetected clumps could eliminate nodes. I think this was a problem because in some anecdotal circumstances, it meant cutting off potential routes. I wonder what happens if I cram a bunch of units onto a one-tile island. Interesting. Before I continue with improving the pathfinding, I want to improve the terrain generation a bit. I see some weird terrain change at the edge of the arena. I think this is because the smoothing function records 4 neighboring indexes for all tiles even at the edges. By using an array list instead, I can limit the number of neighbors. It looks like it didn't work. Well, at least I didn't break the program. I think I'll leave this problem alone for now. But a big way I intend to change the terrain is by adding cliff generation. For this, I can take the range of the neighbor intensities, and if they are varied enough, I can change the tile to a barrier type. I also limit this procedure only to the elevations near the coastal and low-high ground transitions. Now I got landscapes that are even more beautiful. Oh, but my pathfinding is having a problem. It turns out my approach to avoid an out-of-bounds error on the array list had a flaw. ChatGPT suggested something called an iterator to solve the problem. Finding a path for one unit is now mostly fine, but a large group of units trying to find a complex route is a different case. When I tell a group of units to move, each one of them independently calculates their path, and I'm giving them all a command at the same time, meaning the program temporarily freezes as it tries to handle the huge wave of computing demand. My idea for solving this is to have the selected units share the same data. I'm thinking about beginning Dijkstra's algorithm at the destination and moving backwards. Yeah, that sounds weird. But the plan is when the program finds the path for one unit, it keeps going, using the data it's already discovered and calculating more v values until it has found and given all selected units its own route, or when it concludes the remaining units as unreachable. Not wanting to do such a complex step in many sessions, I decided to save it for the weekend. In the meantime, I programmed control groups. Control groups are a way to store unit selections. By holding Control and pressing a number, the program stores a selection of units. Then when I want to select that group of units later, I press the associated number without holding Control. Turns out even this had a bug. But it's Saturday now. I'm not focusing on the bug with the control group, I'm focusing on the daunting task of improving my pathfinding. I made for myself another backup folder with the current code before I make such major changes in a complex system. I started with reversing Dijkstra's algorithm, which I'm calling ArtSkid. That should be an easy fix. I should be able to just reverse the roles of the start and end nodes. That didn't work, so I tried again. And it's at this point in the development that I think. Ironically, going forward sometimes means going backwards. I do some awkward rework to something that works, the program gets worse, but eventually with intelligent thought, I continue in something that natural selection would have discarded, and eventually I get something that is better than what I had before. Maybe this is yet another reminder that macroevolution did not happen. I did some minor adjustments to the new backwards pathfinding and got the same unit behavior that I had before, but I didn't change the program in vain. It's time to get the path brain capable of handling multiple student units. And then I didn't work on the project for a month. There were multiple reasons why, but at least one of them was a valid reason. I wanted to get Viastama Salvage finished for launch. Viastama Salvage is a game I've been working on where you can fly a ship through space, shoot space junk, get randomized upgrades that give the game some variety. Want to play? You can download the game for free on itch.io. Link in description. Okay, but due to me shifting my focus on getting that game released, I've lost some familiarity with my RTS code, so I will be coding this in multiple sessions. I did some troubleshooting and found some errors. I got a single unit moving again, but when I have multiple units selected, one moved properly while the others move in a straight line. Then I think when trying to solve that problem, the unit would move if there was no obstacles, but if there was an obstacle, it wouldn't move. Searched for I think hours and eventually tracked it down to this. The artsget object wasn't resetting the termination permitted boolean variable, so it wasn't resetting when the algorithm ran multiple times for one command. I wasn't planning to mention that to keep the video shorter, but with how much time I lost to that simple mistake, I decided to bring it up in the video. But let me say this. If you're an aspiring programmer, don't let this intimidate you. I made mistakes like this more often when I had less experience with programming, but as I continued, I developed habits for setting up code that is less likely to mess up. I got the pathfinding working again with multiple units and with the program able to notice unsolvable routes. But to my surprise, the program wasn't smoother. In fact, it was running worse. I set up a controlled experiment with the same arena and a number of units. My old code made only 60 segments, while my new code made 420. While thinking through my method, I realized another problem. If two units have different obstacles blocking their paths, my method draws lines between units and obstacles that are not relevant to it. But the method should still be more efficient when there's just one obstacle that is relevant to both units. I decided to continue. Wait, what's that? I programmed the segments to be partially transparent. That means when you see these two lines of different shade levels, the program is drawing multiple segments on top of each other. I figured it out. There were multiple nodes being drawn on the exact same point. This was due to obstacle clumps getting included multiple times, so they would get nodes made multiple times. After a simple fix, I ran the same test and got 33 segments made, nearly half the amount as my old code would make. I made another arena that I think would be even more challenging. My old code made 7,800 segments, while my new code made 1,131. I then did a test that had two smaller groups of units moving toward a middle area. 1,900 segments for the old code, 1,036 segments for the new code. What if I split it up more by having one in each non-middle pocket? 1,428 segments for the old code, 1,332 for the new code. Considering the lesser difference for the spread out groups, I think the new method has some new inefficiencies in some circumstances, but it seems to be worth it. I would also ask the question, which scenario is more common in an RTS? I think it's more common for players to give orders to groups of units that are near each other, which is what the new method is a lot more efficient at, according to my research. So I think this new method was worth making, which is nice for me because I spent a lot of time on it. I also investigated the A-star algorithm, which is a more efficient version of Dijkstra's algorithm, but by this point I was thinking about video length. I think I'll make further efficiency improvements, but I think I've shown enough of that for this video. So if I use A-star, it's going to be on another day. But I have something else. Units getting in each other's way. It's happening even more than in the last episode, which makes sense now that they have terrain to deal with. I see two contexts. One is when a unit is trying to get to a point in a populated area when it can just go to the next point. To solve that, I updated the 1-second check from the last episode. Units now check if the path to the second Dijkstra move is straight, and if it is, it deletes the first Dijkstra move. That one change made groups much smoother. Another context is when a unit gets shoved into a terrain pocket, but I'm not sure how to fix that problem. For now, how about I address the units fighting? I added a new control where the players can press A and click a target location. If a unit is performing an attack command and comes across a nearby enemy, it will automatically go out of its way to fight. And now, it is time. I said I would show a battle to end the video, and here it is. Having two types of units plus terrain ought to make for a more interesting fight. I set up some units for two teams and begin the attack. I eliminate the western satellite units and make my way east. This small group was easy to handle, but then I zoom out and look at the overall map. I wondered if I would have enough units to win, but I would find that out by trying. I get my units in position to tackle the eastern base. My reinforcements are in a nice position to surround the enemy, and then I forget to send each flank simultaneously. I still get the other units there in time to fight, but it's still a bit sloppy. Now for the south base. This was satisfying. Admittedly, it was an easy fight for me, but it was still satisfying to see what I could craft in this program. The battle was not reflecting my skill with playing the game, rather, it was showing the progress with making the game itself. But I would still like to experience the challenge with playing the game. And actually, by the time I've released this video, I've already been making further development of this game beyond what I have shown in this video, including trying to make multiplayer. But even if I succeed, I don't expect me to be making a video like this showing me developing that, because it doesn't seem fitting for this style of video. But even multiplayer aside, I've been making other developments in the game, like giving structures or resources. I added images now. There are still ways I could improve unit behavior, but there are so many that it's impractical to mention them all in a video like this. But I think this video still shows a lot about general pathfinding, and I hope you learned something. Not just enjoyed, learned.